Welcome to part 2 of this Arduino C++ course for model railway control, and today we're going to be looking at servos again. Today we're going to be looking specifically at speed control. So let's have a look at the workbench and I'll try to explain what I'm talking about. So as you can see, I've got 4 servos set up on the workbench. I've got one servo here in a mount that is for turnout control. I've got 2 servos here that are moving together but in opposite directions. These are to simulate, if you like, a crossing situation. And then I've just got this servo down here going flat out. Now, one of the things that you'll notice is that each servo is moving, if you like, in its own speed, its own direction, and none of those movements or speeds interferes with any of the other servos. Now, as always, there is the link to the Digital Town website where you can find the resources for today's lesson. So as we go over to the site, you have some various information. There is the circuit diagram. Click on the circuit diagram and you will get the larger version. Now, one thing about this circuit diagram today, just something to know about servos. These small servos that I'm using, they have what is called a stall current of 500 to 750 milliamps. Now, the stall current, if you like, is the maximum power that the servo will use if you try to physically stop the servo moving. Obviously, on the test bench, I don't require that much power because there is no resistance against the servo. However, if you've got a servo pushing against something quite hard, you're going to use more and more power. Now, this is important because it's very easy to get to the point that you forget just how much these servos are using, and before you know it, your power supply has run out. Because if you had a sort of a 1.5 amp power supply, if you look at that, you're only going to get realistically 3 to 4 servos running before you run out of power if you're working them hard. Obviously, if they are moving a light load, if they were moving maybe a crossing barrier or something like that where there's not much resistance, then they're not going to need as much power. But it's just something to be aware of, that when you're supplying your power to your servos, make sure you've got enough, otherwise they will start to behave a little bit weird. So just going through the diagram, obviously here I have a desktop power supply that's feeding my breadboard. On a layout situation, this is going to come from some other 5-volt supply. You can see that the servos themselves are drawing their power from this supply. They are not taking it from the Arduino. The Arduino 5-volt pin up here can only really power one servo under any kind of load. So obviously the ground also is going to the power supply, but also the ground is from the power supply ground to the Arduino ground. It is very important that all the grounds are connected together, otherwise you will get some very weird scenarios with your servos. Now, for the sake of the diagram, I have only included 3 servos and I've connected them to pins 8, 9 and 10. Obviously on an Uno, realistically, you could use pins 2 to 13. I'm not always so keen on using 13 because of the LED, but you could use all of those pins. If you're using a Mega 2560, obviously you've got a lot more digital pins that you can use. So you could increase this diagram, use as many servos as you want, but your limit is going to be the number of digital pins you have and obviously your power supply. Right, let's get on with the lesson. So sketch 1 is a very basic servo movement, and we're going to be using servo.write to move the servo. So I've created my servo object. I've called it servo1 because obviously I have a number of servos today. Servo1's pin is pin 8. For timing, I'm going to be using current millis. Now, if you go to the Digital Town site, if you don't understand timing using millis, there is a link to a previous tutorial that I've done on using millis for timing. Do not use delay. I know the sample code uses delay. Do not use delay in your code or you are going to finish up with a real mess. Right, so we've got current millis, servo1 millis, which is going to keep track of the time for the next movement. We've got a timer. I am going to move the servo every 2 seconds. And I've also got a variable called servo1 pos, which is the position of servo. I've started the serial monitor and I have just serial printed the name of the sketch. This is so that when I reload the Arduino, I can find out exactly what sketch is running. Then I've very simply attached the servo, basically started the engine, and then coming down to the main loop, I start the loop with current millis and I set that to the current board time in milliseconds. Then we're going to use a typical millis timing system. So we're going to say, is the current millis minus servo millis greater or equal to the timer, which is 2000 milliseconds, 2 seconds. So if that 2 seconds has gone by, reset the timer and change the position. And if the servo's current position is greater than 90, it's going to set it to 10 degrees. And if it's not greater than 90, it's going to move the servo to 170 degrees. So realistically, I'm then going to move the servo. And this sketch is literally going to move the servo as fast as possible between 10 degrees and 170 degrees. And as you can see, this servo down here is now going absolutely bonkers, moving as fast as it possibly can. And you can actually hear it. Probably the mic doesn't pick it up, but it makes quite a noise as it moves because it's literally trying to get there as quickly as possible. Now, if we think about this servo movement from a model railway point of view, there are some things, maybe if I was using my uncoupler where no one can see it, I wouldn't mind the servo moving flat out. However, there are some problems with this. The faster the servo moves, the more noise it makes. So if I want the servo to be quieter with my uncoupler, I can reduce the speed and therefore reduce the noise. If we were simulating a crossing barrier, if your crossing barriers were attached to this servo moving at that speed, in real life they would just throw themselves off and snap in half, and might well do the same on a model railway. If we're using this for turnout control, even then it's not great to move the servo at full speed, because as the wire gets to the end of its movement, I've got handmade points. It would be quite nice if the servo moved the turnout slightly gentler. Also, if you watch videos on turnouts moving in real life, I've been watching some videos of signal boxes, and on the whole, it takes sort of 2 to 3.5 seconds to move the turnout in real life. If it's an old-fashioned signal box, there's some poor guy who's got to push the lever, and with modern railways, with I think they're usually electric motors that move the turnouts, even they don't move them flat out because they've got some gearing in so that they can use smaller motors, and long turnouts weigh a lot. So it would be ideal in all situations to be able to control the speed of the servo. Now, if you're new to using servos, you tend to go into the examples, go down to the servo library. As you can see, I've got rather a lot of libraries installed. Go down to the sweep example. And in the sweep example, it basically moves the servo from one position to another position. And in the example, they use a delay of 15 milliseconds. Now, this is a great sort of example of how to move servos, but using delay is an absolute disaster, especially when you want other things happening. In the time period that the servo starts this for loop until the end of this for loop, basically for 180 times 15 milliseconds, the Arduino can do nothing else. It then goes straight into this second for loop. So again, it's 180 times 15. So bringing up the trusty calculator, if we go 15 times 180 equals 2,700, which is 2.7 seconds. Now that means from when this for loop starts to when it ends, your Arduino can deal with nothing else except the movement of that servo. It will not respond to any button presses. You're going to have problems if you're sending DCC commands. It's just not going to work. If you're now going to move it twice, that actually means for 5.4 seconds, nothing is going to happen. So although this demo sketch shows you how to move the servo, using delay is a very, very bad idea if you want multiple things happening at the same time. So for the second sketch, what we're going to do, hopefully you can just about see the servo moving. It's moving slowly in one direction and then slightly faster in the other direction. So let's have a look at the code on how that's done. So this is sketch 2, and we're going to move the servo between two angles in a time period. Now, as always, you can download all of the code for today's lesson off the Digital Towns site. Right, let's get back to the sketch. So we're going to create the servo object after we've included the library. I'm on pin 8 again. Current millis is going to store the board time. You'll find in all of my sketches, current millis always stores the board time. We then have the servo 1 position. We then got a variable, an unsigned long for servo 1 step millis. This is going to keep track of when the servo has got to take, if you like, its next step. I've got a timer. This is going to give me the time between the steps. I've got a destination angle. That is the position I want the servo to move to. And I also have the current angle, so I know where the servo currently is. Coming down to the setup, once again, just start the serial monitor and I serial print the sketch name. And then I attach servo 1. Right, let's get into the main loop. So let's start with this little bit here. So current millis stores the board time in milliseconds since the board started up, and it is this part of the sketch that controls the servo movement. This section down here is just about setting a new direction for the servo to move in once it's reached the end of its movement. So all we're doing here is we're checking, first of all, is the, if you like, the target angle not equal to the current angle of the servo. So the servo is going to move between two positions in 1 degree increments because we're using servo right. So it's checking here. We're aiming for an angle and we are currently at an angle. If they're not equal, then the servo still has to move some distance. Then what it is doing in this next section, if you're used to timing with millis, it's just checking, is it now time to move the next step, or do I just skip and go round another loop? If it is time to move to the next step, then if the target is greater than the current angle, then we need to increase the current angle. And if obviously the servo is moving the opposite direction, which would mean that the target angle is smaller than the current angle, then we need to decrease the servo 1 step current angle. And then all we're going to do is servo right. Now what that means is basically every time we servo right, we're going to have increased the angle or decreased the angle by 1. So that is the movement control, and as you can see, it's quite a simple sort of set of if statements. Down here is some code that I'm just using to give the servo a new position to go to. So this, as it says here, would normally be replaced by a button or a DCC command. I'll start to add that in, I think it's 2 lessons time. We're going to look at PCA 9685 servo control next, and then we'll start to look at how the buttons can be used to control servos using just the servo library or the PCA 9685 board. So all this is doing is it's saying if the servo angle and the current angle are the same, so in other words, the servo has now finished its movement. If it's greater than 90, then set the servo to go to an angle of 10 degrees. And I want it to do it in 1.5 seconds, 1,500 milliseconds. Else, if it's, if you like, at the other end, I want it to move to position 170, and I want it to do that in 10 seconds. So in one direction, we're going to move to an angle of 10 degrees, and we're just going to do that quite quickly in 1.5 seconds. The opposite is we're going to move to an angle of 170 degrees, and we're going to do that in about 10 seconds. Now, this is where things get interesting. How do we work out the timing? And this is where this little function here works out how many steps the servo needs to make. So it works out where the servo currently is, what the new target is. It then knows how many steps it's got to take, and we're going to serial print out how many steps it has got to take. And then we use the time, and we then work out, if you like, how much time it's going to take between each step. So we've got the total time, which, let's imagine we've got 10 seconds and we're going to move 100 and whatever degrees. Divide that out, and that will give me the time per step, and that is what is going to be used in our main statement here that controls the movement, because it now changes this value of the timer. So that is all this little piece does. Let's see it in action. So here we see the code running, and you can see here the number of steps is always going to be 160 because I'm moving between an angle of 10 degrees and 170. However, if it's moving slowly, as it is right now, that's because it's taking 62 milliseconds per step. When it's moving quickly in the other direction, as it's going to do right now, just gets to the end, goes to 9 milliseconds per step, and then goes back to that 62 milliseconds per step. Now, I've just tried to zoom into this servo just to show you one issue with the method that I'm using. If you watch very, very closely, it's quite hard to pick up on the video, but as it's moving slowly, because it's moving in 1 degree steps, you can actually see almost some tiny jumps. Now, it's very hard to pick it up when it's just moving the servo on its own, and to be honest, you wouldn't notice. If it was moving a turnout or something, it wouldn't show. However, if you were building a crossing barrier, these little jumps will actually start to show on the length of the crossing barrier, it will start to look a bit like the second hand on a watch, and you will actually start to see the individual jumps. So in this next sketch, I'm going to show you how we can smooth the movement out even more. So I've got the first sketch up. That was the one that just basically moved the servo backwards and forwards between a position of 10 and 170 as the angle, and that uses servo right. Now this sketch on the right, when it moves the servo, is going to use servo.right microseconds. Now you will notice that this sketch, we're going to move it between 10 degrees and 170 degrees. This sketch is a little bit weird. We're going to move it between a position of 800 and 2000. Let me explain what is going on here. So in the last lesson, when we looked at how servos work, they receive a signal, pulse width modulation, technically between a value of 1 millisecond and 2 milliseconds. In reality, manufacturers don't quite stick to that, and the servos that we're using today actually use between, I think it's 600 and 2400 milliseconds. Now, even between 1 millisecond and 2 milliseconds, we don't have to use milliseconds with the Arduino. We can use microseconds. Now, that means the angle change is in 180 steps. But if we went from 1 millisecond to 2 milliseconds in microseconds, that means we would have 1000 steps between 0 and 180. So we can make the servo move in much smaller steps. Now, because the manufacturers actually start at 600 and go to sort of 2400, we finish up, rather than 1000 steps, we actually finish up with about 1800 steps. Now that means that for every step that we take using servo right to move 1 degree, with servo right microseconds, we can move the servo 10 times per degree. So going to the servo library reference, and whatever libraries you're using, you can usually do a search and find the reference for these. And these are the different methods that you can use in the library. Most people will use servo right, but as you can see, there is this servo right microseconds. And I mean, here they're using values between 700 and 2300. I've found, I can get sort of 600 to 2400, and it seems to work well. Again, you can tweak these figures as you'll see later, but basically it means we can now move the servo in much finer steps, and that should make, if you like, less jerkiness, especially when moving things like crossing barriers. So loading the sketch up, I'm just moving it between these two values at the moment. As you can see, it's moving as fast as it can, and it looks just as it did with the servo right. The difference is now we're using servo right microseconds instead of servo right. Now there is another issue, of course, trying to work out in your head the angle that equates to 800 as a PWM signal and 2000 as a PWM signal is not something that's very intuitive. So in the next sketch, we're going to look at how we can still input the variable as an angle, but still use the benefit of the smoothness of the servo right microseconds. So for our fourth sketch, you'll notice this time I've got these definitions, and these are the servo min and the servo max. On the servos I'm using, they seem to work on a PWM signal between 600 and 2400. Technically, they should run between 1000 and 2000, but they don't. So these are the figures that I've found that work really nicely. And again, you can tweak these slightly depending on your servo if you're finding it's not moving the full sort of 180 degrees. As before, we're going to include the servo library, servo object, pin 8. Instead of current millis, we're going to use current micros. Now, one of the things you need to be aware of with microseconds, numbers start to get very, very big very, very quickly. So you just need to be aware of that in your calculations, and quite often you finish up having to use a long rather than an integer. A integer runs from, was it minus 32,768 to 32,767, whereas the long will go up to over 2 billion. So you can use much, much bigger numbers. If you don't use a big enough variable, you will find what you get called an overrun. And all of a sudden, when you get to 32,767 plus 1, it then becomes minus 32,768. So make sure your variable is big enough. Right, so we've got our servo one-step millis, our timer, our angles, and this is still the servo one-step target angle and the servo one-step current angle. Attach the servo as normal, and now we come down to the main loop. And as we start in the main loop, if you notice, the movement system looks very, very similar. The difference is that instead of current millis, we're now taking the board time in microseconds. Now, there is something you need to be aware of with microseconds. They are very, very small periods of time. Now, that means that if you start to use serial print, you need to be very, very careful, because if you send too much data to the serial buffer, you can actually overflow it very slightly, and you will create a lag that is noticeable in the movement. So I'm using serial print here just to show you what is going on. But when you're running what I would call production code, you need to make sure all your comments are removed. And if you try to use delay anywhere, you will mess the movement up big time. So the actual movement is quite simple. Once again, it's checking, has the servo got to its desired angle? This time, of course, it's that PWM value that it's looking for. And if it hasn't, is it time to take another step? The reason we're using microseconds rather than milliseconds is that the number of steps means that you just get a better figure. Using milliseconds, you have some odd rounding issues that happen, whereas with microseconds, I've got a magnification, if you like, of 1,000, so I lose those rounding issues. Once again, it just knows whether to increase the angle or decrease the angle, and it then servo.write microseconds the next angle that it's supposed to move to. Now, the next part of the code, again, this would usually be triggered by a button, but again, it's going to show you how I am going to, if you like, send the angle rather than the PWM value. If we go to our diagram, to make this work, I need to send, if you like, the PWM frequency, but it's much easier for us as mere human beings to deal with. I want to send an angle between 0 and technically 179 degrees. So let's look at how that's done. So ignore this little bit at the moment. This is sort of halfway through the movement. This is just because I'm not using a button. I'm going to use a timer for this. But what I want to do is I want to send the angle of 170 degrees, and I want it to move in 1.5 seconds. The other angle I want to send is 10 degrees, and I want to move in 10 seconds. So basically I want to replicate sketch 2, but using the right microseconds rather than the right angle. So I'm going to serial print out the angle that I have decided on, and then I'm going to use map. Now you'll notice that what this does is it takes the angle that I've given it, and that is an angle between 0 and 179, and that maps it against the servo min and the servo max. So that range, if I put my cursor over it, you can see is between 600 and 2400. So obviously if we put 0, that's going to come out as 600. 179 is going to come out at 2400. So sort of 10 degrees is going to be probably what, 700, something like that. So as you can see, it will map the new angle, and it will then return that as my servo 1 step target angle that will then go into our movement system. So this is just going to work out, so that's worked out the angle as a PWM frequency, saving us some hassle. And then we are going to take the movement time and once again do a little bit of mathematics to work out the time per step. So as we can see, the servo is now moving and we're getting our various bits of information in the serial monitor. I'm just going to stop it moving. And we can see that when I set an angle of 10 degrees, it then works that out as a PWM frequency of 700. The move time is 10 seconds. The number of steps it's now got to take, it's worked out as 1,609. So it now knows that the time per step when it's moving slowly is 6,215 microseconds. So that would be 6.2 milliseconds. But obviously it's going to round the end off. If we're going the other direction, 170, the system has worked out that that's going to be a PWM frequency of 2,309. The move time is 1.5 seconds, 1,500 milliseconds. It's then going to require again 1,609 steps because it's moving the same distance, but you'll notice it's now got to do that at 932 microseconds rather than that 6,215, and that's why the servo moves quicker in the one direction than the other. So although we've got the movement working at this point, obviously it's only working for the one servo, and that would mean if I wanted to run my 3 or 4 servos, I'm going to have to repeat this piece of code multiple times. Now that is going to get very, very messy, and if you sort of wanted to get up to 10 or 12 servos, that is going to start to look absolutely horrible. So what I've done for the next sketch, I've reduced all this down to some very, very simple functions that you can just call, and everything else is going to happen automatically. So here we are with sketch 5 running. As you can see, I've got my 2 servos here running to simulate a crossing gate, and at the same time I've got this servo here going like mad. This one is not included in this sketch. I just added it later just for a bit of fun. So sketch 5, we're going to be moving servos between different angles using microseconds. One of the things, again, I've put in a note here, just a warning, be careful with your code, because if you start putting delay in anywhere, you're really going to mess this code up. We've got our definitions for the limits of our servos. Again, we don't have to worry about that. And then I've got another definition here. And in this case, it's equal to 3, because at the moment this sketch is using 3 servos. Now, this system is going to start to use arrays. Don't panic. If you're not the greatest with arrays, don't worry, because everything sort of happens automatically for you within this sketch. Now, the reason I have to use a definition here is that if you wanted to change the sketch to 4 servos, if you change this value to 4, then where we have num servos, if I put my mouse over there, you can see the definition num servos 3. When the compiler runs, it does a search and replace within the sketch, and everywhere it sees num servos, it's going to put the value 3. Now that's important, because when you are setting up arrays, you can't set up the array with a variable in there, so you need to use a definition. Don't panic if you don't understand what that means. All it means from a practical point of view is that the number of servos that you want to use within your project needs to be listed here, whether that be 1, 2, 3, 10, 12, however many you want. Just make that the value of num servos, and it will do everything else for you. Now, in the previous sketch, we set up a servo object and we called it servo1. This may be a bit weird, and you may have never seen anything like this before. This is a servo object array. So this is going to create 3 servo objects in an array. A little bit difficult to get your head around, and you don't need to worry about how it works, because it's all going to happen automatically. The only other line that you really need to edit from a setting up the servos is this one, which is the array of servo pins. Because I have 3 servos, I've used pins 8, 9 and 10. If I change that to a value of 4, then I can just add another servo in just like that. But of course, you need to make sure that you have changed this value here, or you're going to get a compilation error. I've left current millis in because very often when I'm building a project, and certainly later on when I add buttons to these projects, we're going to need current millis for the debounce. But we've also got current micros for our timing. Now, instead of setting up our different variables as in the last sketch, we're setting up the variables, but in each case it's an array. So instead of storing 1 variable, it's going to serve, in this case, because we've got num servos equals 3, it's an array of 3 elements, so it's going to store 3 values. If I change this to 4, then this will store 4 values. Change it to 10, it's going to store 10 values. So that's why I say, where, if you like, all the hard work has been done automatically, you just need to leave these items in, and the only lines that you need to worry about editing are the number of servos and making sure that you've got your list of pin numbers. So now coming down to the setup, this is a little bit strange in that there is a for loop, and the for loop is going to attach all these servos in one go. Again, because it uses this num servos definition, if you change the number of servos, it knows to add more loops to the for loop. So all the servos are going to get attached in one go. Now we come down to the main loop. Now the main loop, I put current millis in because we will use it later for debouncing buttons and things like that. And we've also got current micros. I've then got one single function call, which is servo movement control. This calls a function down here. Let's just scroll down to it. Servo movement control. This will control as many servos as you add to the system. This is going to cover all the servos. If you notice, it's got a for loop in here, so it's going to go through each servo one after another very, very quickly, and it's going to check if any of the servos need to move. This means that you can have sort of as many servos as you've got pins for, and each servo's movement is all going to be controlled by this one single function, which means that in your main loop, we simply have to make sure that this servo movement control function is called. That's it for the control of movement. The rest of this is just to do with how I have set the movement of the servos. Now again, these would normally be controlled by buttons. Let's just get rid of that lot. So the way this would normally work is you would have a button or something that when the button was pressed, you would call this function here. And this is to move two servos. Again, I've created a function specifically to set up the movement of a servo. So what we do to move the servo, coming down to that function, just so you can see the variables that need to be passed, we have the servo number. That is the number of the servo in the array. So in the array, 8 would be servo 0, 9 is servo 1, 10 is servo 2. With arrays, you always start with 0. So again, if you added more servos, just keep adding them on. So this function, all it requires me to pass to it is that servo number, the destination, that is the angle that I want the servo to move to, and the duration, that is the time that I want the servo to take to get there. Now, I think I've put some notes on there. It is the time to get there in milliseconds. I didn't want you having to write it in microseconds, because microseconds, you'll miss a 0. Everyone does. I do it. So let's stick to milliseconds, the angle in degrees, and the servo number in the array. Once you've put that information in, the system here will basically do the mapping for you as before. It's going to work out all the information, update the array as needed, and your servo will start moving. Now, if you want to test this out, feel free to uncomment the serial prints. However, there are a huge number of them, and because there's so many of them, when I've got 3 servos running, when it sets a new destination, because the buffer overflows slightly, I can actually see if you like, the servos stop for a very, very short period of time. It becomes more obvious as the movement is finer. But that's why they're commented out, but feel free to uncomment them if you want to see it do all the calculations. Now, what that means is, in the main loop, obviously, as I've said before, that is the control function. These would normally be controlled by a button. So what I'm doing now is I'm saying, once it's got to the end of the movement for these 2 servos, give it a new movement. But we could have this, digital read a particular pin. If that pin has now gone high, if a button has been pressed, then we're going to just add this function in. Set servo 0. I want it to move to 10 degrees and I want to do it in 4 seconds. Now you'll notice, because this is those crossing gates, it's going to set 2 servos, 0 and 1. One of them it's going to move to 10 degrees, the other one's going to go in the opposite direction, so it's going to 170. Again, it's going to do it in 4 seconds, and of course once it's reached the other end, that's going to swap over and they're going to go back. And then that other servo, the white one that's moving very, very quickly in the bottom right of the video, that is our servo 2. That is moving between 60 and 120 degrees, and it's doing it in 200 milliseconds. Basically, when you get down below a certain value, the servo is moving as fast as it can, because if I set this value to 10, the servo cannot physically move in 10 milliseconds from one position to the other, so it will just try and move as fast as the servo can physically move. So now, as we can see, we've got those 2 servos doing their sort of movement in their 4 seconds, whereas this is trying to do it in 0.2 of a second. Absolutely impossible, so it's just moving as quickly as possible. Now I have included a version 6 of this sketch, and that's the one where I've now added my other servo in, just so you can see the difference. So on the left hand side we've got the 3 servos. Again, I've now changed it to 4 servos. The original 3 servos, pins 8, 9 and 10, and I've added an extra servo on pin 11. And then the only other change that is made in the whole sketch is coming down to the main loop. He says looking for it rapidly. There we are. This is the original sketch, and then in the new sketch all I've done is, that was servo 2, the one that's moving quickly. Then for my next servo, servo 3, I've just called it to move servo 3 between an angle of 73 and 117, and I want it to move in 2.5 seconds, because if you now watch the video, 2.5 seconds seems about right for the turnout movement. You can see it just moving backwards and forwards, turning the micro switch on and off, because on my layout I need the micro switch to change the polarity of the frog. But as you can see now, we now have 4 different servos, all running in their own directions at different speeds, and each of them can run simultaneously through very, very few lines of code just by calling a couple of functions. So I hope that's been helpful for you, and you can now start to see how easy it is to use servos to get very smooth speed control out of them. There will always be a very slight degree of jerkiness depending on how nice your servos are. Some manufacturers do a better job than others. Some of the jerkiness, I think, is actually down to the roughness of the gears, and I'm sure some of them will bed in over time. What we're going to do now, in the next lesson, I'm going to show you how to use servos with the PCA 9685 servo driver board, and then the lesson after that we'll start to look at how to control these functions with buttons. So once again, thanks for watching, and please click the like and subscribe, because it really does help the channel. So thanks for everything, and I'll see you in the next video. Bye for now.